All right, this next example is about identifying an extraneous solution. So guess what? We're going to have an extraneous solution on this one. So let's see what that looks like, how we deal with it, how we figure out what our true solutions are. Part A, solve the radical equation. The square root of 3x minus 2 is equal to x minus 4. So to solve any radical equation, you want to isolate the radical, which it is. There's nothing outside of this square root, which means we can undo the square root. We are going to square both sides. Have you noticed how I always put parentheses around the entire side when I square it? This is where that makes all the difference. If we don't have those parentheses, we're going to do some different math and get a wrong answer. So when you square the square root of 3x minus 2 on the left side, it leaves you with 3x minus 2. Now what's happening over here is we're not squaring 4 times x, we are squaring an x minus 4. This is a binomial. When you square a binomial, that means you actually have to multiply out x minus 4 times x minus 4. I cannot bring the squared in to these terms like we've done with some other problems because it's a binomial. Just a nice little hint, if you see any addition or subtraction inside parentheses, you cannot bring your exponent in. You get the wrong answer. So please be very, very careful about that. All right, we're going to multiply this out. X times x, x squared, x times negative 4 times x, and negative 4 times negative 4 is positive 16. So I'm going to write the answer over here. I will combine like terms as I rewrite it. So we have x squared minus 8x plus 16. Okay, so we have an x squared equation. When we have x squared equations, we have to change our solving method. We're going to try factoring first. If that doesn't work, then we're going to try the quadratic formula. So both of those methods mean, or they require that your equation is set equal to 0. So I'm going to go ahead and subtract 3x from both sides. I'm also going to add 2 to both sides, and you can see I'm kind of lining those up below their like terms. Your 3x's cancel, your 2's cancel, leaving you with 0 equals x squared. Negative 8x minus 3x is negative 11x, and 16 plus 2 is 18. So the first method we're going to try to use to solve is factoring, because it's much faster. If we can recognize that this is factorable, we'll have our answer pretty quickly. It is just an x squared trinomial, so we can go straight to our c value. Do we have factors of 18 that add up to a negative 11? And if you think through your factors, we get a negative 2 and a negative 9. So x minus 2 times x minus 9. Now we use our zero product property. When you are in factored form, you set each factor equal to 0. And solve. So when you solve for those, you're going to get x equals a positive 2 and a positive 9. So we got 2 solutions, which when you have an x squared equation, we can expect 2 solutions. Are they both solutions? Is just one a solution? Are none of them solutions? The only way for us to know what our true solutions are will be to check both of these answers. So we're going to check first, does x equal a 2? So we go back to the original equation. We have the square root of 3 times 2 minus 2. We want to know if that equals, on the right side we have x minus 4, so I'm going to plug in a 2 for the x, so 2 minus 4. Again, don't cross your equal sign when you do your check. Just simplify the left, simplify the right, see if you have a true statement. So 3 times 2 is 6. 6 minus 2 is 4, so we have a square root of 4. On the right side, 2 minus 4 is negative 2. All right, back to the left side, we can square root the 4 and we get 2. Carry down on the right side, we get a negative 2. 2 does not equal negative 2, so I'm going to say that the 2 was not a solution. That does not automatically mean that 9 is a solution. We have to check to see if 9 works as well. So we're going to do one more check. This time we're going to check to see if x equals a 9. So we go back to the original equation. We have the square root of 3 times 9 minus 2. We want to know if that's equal to 9 minus 4. Again, just simplify your sides separately and see if you get a true statement. All right, so underneath our square root, we have 3 times 9, which is 27. 27 minus 2 is 25, so we have the square root of 25. On the right side, 9 minus 4 is 5. Square root of 25 is 5. On the right, we have a 5, so that worked out. So x equals 9 was a solution. So final answer, x equals 9. We got two solutions mathematically, but that's because an extraneous solution came up in our solving process. And when we plugged it back in, we could tell it was not a true solution. So why does this extraneous solution arise? Our first step in solving the equation in part A was to square both sides to get this. That was in our solving. Now you have two equations. So when we squared this side, we had this left us with a 3x minus 2, and this left us with the x squared minus 8x plus 16. Are they equivalent? You can use the graphs to represent both equations. So here is the original equation. If you graph this function and graph this function, any intersection points will be the solution. So the square root of 3x minus 2 is this right here. And then x minus 4 is this blue line. You can see they are only crossing in one spot. And there's that x equals 9. That's the solution when you set them equal to each other. We're solving for the x. So the 9 of the ordered pair is our solution. Now, if you square both sides, that does change what the equations are. This square cancels out the square root. It turns into 3x minus 2, which is this red line right here. And when you square a binomial, you get, well, actually, this is vertex form, x minus 4 squared. It's shifted to the right 4, and it actually is a parabola. So you can see that squaring both sides changed the functions just enough that now they are crossing in two spots, where the original equation had them crossing in only one spot. So this x equals 2, that was our extraneous solution, but here you can see we're getting that x equals 9, the true solution. So our conclusion, the equations are not equivalent. Squaring both sides did create that extraneous solution.